All right, I think I'm going to get started. So today we're going to start talking a little bit more about sort of aromatic compounds, and we're going to start getting into a little bit more of sort of reactivity of benzene and sort of benzene derivatives. Before we get into that, I do want to just talk about a couple, not big on nomenclature, but I think there are always sort of important terms that we use a lot and that we should probably discuss. And one in specific that will become important down the road. And so we'll just sort of briefly talk about nomenclature of benzene. Okay? And so there are certain benzene derivatives that you'll see come up from time to time that have names that are probably worth knowing. And some of them might be fairly translatable based upon your knowledge of things. And so I just wanted to sort of discuss a few of these. Right. So if you have benzene that has a carboxylic acid connected to it, that's going to be benzoic acid. You guys might already know this. Benzoic. You guys might already know this because you've worked with benzoic acid in labs quite a bit. That's the sort of fortunate thing about a lot of these compounds. Another one that you'll see a lot, right, is this one. This is toluene, and so you'll occasionally see toluene sulfonic acid. So paratoluene sulfonic acid, for example, is an acid that we'll see time and time again. And some of the others, the one other that may come up from time to time is going to be aniline. Okay, so aniline and phenol, I'll just bring up those two. So this compound is phenol, and the sort of equivalent of nitrogen is aniline. Okay, and so here's just four examples of molecules that you'll see from time to time in terms of names that are given to compounds that come up fairly commonly. So again, you've already seen benzoic acid comes up a lot. Phenol will come up quite a bit. Aniline perhaps a little bit as well as toluene. So that's worth it. I think your book has a few more molecules. These are really the four that I think are probably important to know. And aniline's not even too important, but specifically these three, just because they'll come up from time to time. All right, so once we start getting into substituted benzene derivatives, this is where if you have molecules, I don't even really care about this that much, but if you have molecules that have like three, and you can read about this in your book, right? So if you have a molecule, let's say, for example, got three groups, sort of like three groups on a benzene ring, you sort of want to have some name that goes along with this, right? And so generally what happens is you sort of number it, and you number it based upon whatever's going to have the lowest overall sort of numbering scheme, right? So what you don't want to do is we sort of went this way, for example, and we started numbering them 1, 2, 3, 4, 5 versus 1, 2, 3, 4. That's going to be the bigger set of numbers, right? And so we can imagine two numbering systems that keep the biggest number small. That could be going from 1 to 4, or we can go the other way, 1, 2, 3, 4, right? And so in this case, you're still going to sort of keep the numbers low, right? So you've got a 3 versus a 2, so we'll go with the starting from here as being 1. Again, just because the 2 here is the lowest, right? And so we effectively numbered where our groups are here. And then when we sort of name them and sort of write the numbers from them, you guys remember from last semester, you'll oftentimes now go alphabetically. So again, this doesn't say anything about the chemistry, so I don't really care that much about it. But we have a nitro, chloro, and a bromo. Okay? And so in this case, one of the ways that you can name it would be sort of 4 bromo, chloro, C becomes before that, so 2 fluoro, 1 nitrobenzene. Okay? So again, I don't really care too much about nomenclature. I suggest to you guys, in all honesty, to just sort of think about it and maybe read through it before your MCAT or something like that, because I'm sure that if we go through rigorous analysis of IUPAC, you'll all forget it within the next year and a half. And again, IUPAC really doesn't teach you anything about the chemistry in terms of the foundation. Now, there is one aspect to the nomenclature that is important, at least in terms of us moving forward and being able to communicate. So we're never going to start naming compounds in IUPAC form in this class, but what we will be doing is talking about relative positions. Okay, and so in the same way that substituents being cis or trans, right, have become important parts of our vocabulary in chemistry, anti and syn, sort of terms that are referring to two substituents, these are important things. In the same way, as we're going to see when we're discussing aromatic compounds, there are terminologies that refer to the positioning on that benzene group that are going to be important. Okay? And really what we're talking about is groups that can either be next to one another, ones that are sort of what we might call 1,3, or one carbon separating the two. Or across one another. Okay, so here's the 3 possibilities when you're talking about 2 substituents. There's really 3 different ways that they can be, again, because then if we start continuing to go in the other direction, then it would just be sort of reverse of what we were looking at. And so these are terms that we're going to want to get to sort of know, okay? And the terms that we're going to use are ortho, meta, and para. Okay, so these are, and oftentimes when we see them, if you, for example, read a molecule, right? So like, sometimes you'll see a letter that sort of talks about certain substituents, and all that is sort of like a little italicized O, a little italicized M, or a little italicized P. And so you'll see lowercase o, lowercase m, lowercase p in a sort of italicized form, oftentimes in terms, and that's going to sort of tell you what the positioning is. So for example, 2 common things that you would see would be a molecule like okay, so you'll see a molecule that are called M-chloroperoxybenzoic acid, right? So you guys have seen this in the past. This is MCPBA. Okay, and what it is, right, is peroxybenzoic acid, right? So that's a peroxybenzoic acid. And then there's going to be a chloro on here, and the chloro is going to be at the meta position, right? And so metachlorobenzoic acid. is going to be that structure there. Okay. Another place where you'll sometimes see this sort of designation would be a molecule like paratoluene sulfonic acid. Okay, and so as we sort of just wrote up there, right, we know that toluene is this group here, right, and so paratoluene sulfonic acid is going to be this molecule with a sulfonic acid on it, and it's going to be at the para position, right, so this is paratoluene sulfonic acid. It with the P, okay, so again, these are just things to sort of learn. This should be your sort of understanding of this and the language in a way will be parallel to, again, like I said, understanding cis-trans is going to be important to that extent, understanding syn or anti, which simply, or even to an extent, endo-exo to an extent, which effectively says what relationship one molecule has within itself. Okay, so these terms will come up as we start talking about reactivity of benzene groups because there'll be certain directing effects that we'll discuss perhaps later on in today's lecture, possibly next lecture, that are sort of dictated based upon different substitutions and where that substitution pattern will go. Okay, so that's it for nomenclature. All right. So now, we saw in first semester organic chemistry, we began to talk about stability of, for example, cations, right? And as some of you might remember, this sort of tertiary carbocation is the sort of most stable, but sometimes secondary carbocations, if, say, for example, they have a lot of resonance stabilization, might be comparable, right, in terms of the stability. So you might imagine a molecule like this might actually have comparable stability to, say, for example, a T-butylcation. And the reason for this, right, is why? Right, resonance, right? So there's a lot of resonance forms that you could draw throughout this structure. So we can continue to stabilize that carbocation all around this ring. Right, and we can keep going around and around and around, right? So these carbocations are extremely well stabilized throughout these systems. As it turns out, this ability to sort of stabilize positive charges, you can also see with negative charges, right? So if you would imagine a situation where you might have I don't know, let's say, whatever, we'll just do the parallel, right? You might imagine that by the same extent, these protons might be a little bit more acidic, right? Because if you deprotonate them, right, now you can move these electrons throughout the system here as well. Right, I can keep pushing this around and on and on and on, okay? So the position that is, does anybody remember, we might have sort of said this, but really not spoken to it. Does anybody remember, in general, sort of what this sort of position would be called, or maybe this carbon? Right, so this would be sort of called the benzylic position. right? And again, we'll see things like benzyl alcohol. Again, benzoic acid is simply an acid at this sort of benzyl position, carboxylic acid at that sort of benzyl position. And so it turns out there's a lot of factors that arise due to the ability to sort of stabilize through resonance these groups. And while it's not perhaps benzylic per se, we can start to think about some of that stability by thinking about the pKa of phenol. Okay, so phenol is a molecule with an OH, right, with a hydroxyl on that aryl group. And if you sort of think about deprotonating this molecule, right, if you treated it to some base, what we would end up with is sort of, we call it a phenoxide, or this sort of O- group on it, right? And just as I sort of pointed out over here in terms of an alkyl anion, certainly the alkoxide can undergo a variety of different resonance stabilization forms as well. Again, even though we're pushing them away from the oxygen, we're breaking aromaticity and so forth, this is still a stabilizing factor. Okay, and so again, we can keep pushing that around the ring, right? The point is that this sort of stabilization by resonance of this OH bond being deprotonated, again, that sort of anionic oxygen can sort of delocalize that charge throughout the sort of pi system that's attached to it. And so in this case, this is, you can sort of visualize it, you can see it, but it turns out that there is physical properties to this as well. And what you see is that the pKa of, say, for example, phenol, right, would be about 10. Okay? And that's a little bit different than, say, for example, methanol, right? What's the pKa of methanol? Everybody remember? 16, 17, somewhere in that ballpark. Water is about 15, right? So you can see that you pick up a few orders of magnitude pKa units, and so it becomes that much more acidic simply due to stability. In fact, when I was a postdoc, I was working on a probe. We ended up coming up with another way to make it, or a different molecule that was easier to make, but at one point I had a molecule that looked something like this that I was trying to aromatize. I forget if it was exactly like this. This is just sort of general idea. And I was able to leverage the relative pKa differences between this phenol, right, and this alkoxide. And what I was doing, all I wanted to do was put a protecting group on there. And I think the protecting group that I put on there was maybe a TBS group. And if you just use sort of TBS and triethylamine or something like that, it didn't really work out so hot, you would get a mixture. But if I just sort of used one equivalent of, I believe it was like sodium carbonate or something like that. I believe this was what I used. I don't remember exactly, it didn't work out that much. But you can imagine if you use a base, right, and you just use one equivalent of that base, right, what's going to happen is you're going to generate the more stable anion. So what I did was I effectively premixed this compound with a base, right, to sort of generate the more active alkoxide, right, and then what I was able to do is take this and treat this with TBS chloride, or maybe it was TBS iodide, I don't really remember, but the point is that I was able to functionalize this group really well, and I remember this reaction worked pretty well. And so this sort of takes advantage of the sort of relative acidity, right? You could tune the electronics of the system. Again, you have two groups that otherwise might be comparable in terms of their nucleophilicity, but what you could do, and what I had done during my postdoc, was I sort of leveraged and this is, I come up with this has been strategies pretty well precedent in the literature, but you basically attenuate the electronics of this phenol by deprotonating it, making it anionic, thus making this a better nucleophile and giving yourself selective deprotonation. So here's sort of a real example of where this type of stuff worked. So this is one of the advantages, or not advantage, but I should say one of the differences of phenols, and an example of where in a synthetic context you could actually leverage those differences for your advantage in terms of selectivity. Okay. Now, as you might imagine, because of the sort of conjugation, there can actually be some differences, and I just wanted to talk about this really quickly to get us thinking about how substitution patterns can have an impact on relative reactivity or stability within aromatic systems. Okay, so if I had two different right, so if I had two different nitrophenols, they're both going to be pretty acidic, right? And so it turns out that, as you might imagine, both of these are going to be a little bit more acidic than phenol, right? Because you've got this sort of electron withdrawing nitro group, okay? But one of the interesting things about aromatic groups is that oftentimes the relative substitution can have a dramatic effect on the activity. And so in this case, this would be meta substitution, right? This one would be para substitution. Okay? And if you were to look at these two, which one might you think would be more sort of acidic? And I could see a couple different answers, so I'm kind of curious. Yeah. So I'm hearing a vote for meta, and what would be the reason why you might think meta might be more stable? Let's just say more acidic. Let's just talk about the alkoxides and think about stabilization. Right. So here's the first 12 electrons. Here's the second one. We want to keep going. We can get to this one, right? So those are really the three possible resonance forms that we can have. Madi. All right, so let's start looking at this other one, right? And so I'm going to, for the sake of time, I'm just going to push the electrons a little bit. So I can push the electrons onto this one first. Oh, whatever, I'll push it. Time. Okay, so that anion, and then what we can do is we can push them onto that carbon. Right? And then as Monty's saying, what we could do is now at this position, now we have an additional resonance form, right? Where we can actually push this up into the nitro group. Does everybody see that? Yeah, so, and it turns out that, and again, we'll see this is one of the, I think, keys, sort of recognizing these different forms ends up being, I think, one of the keys to, and then again, we can push it to the other side as well, but the point is that there's effectively a fourth resonance form that this sort of nitro can have, so you can, in fact, bring that negative charge up onto another atom. And in fact, the other atom that you're bringing it onto is an oxygen, right, which is more electronegative, so it's an even better resonance form. But really a key to, I think, in general, the aromatic chapter, as we'll see, is going to be sort of recognizing sort of these resonance forms and how those resonance forms may stabilize different groups in different processes. And so in this case, what we see is that, in fact, the pK of this one is about 7, whereas the pK of this one is about 8. Right, so it's about an order of a magnitude more acidic than the other. Again, they're both more acidic than phenol because they both have an electron withdrawing group. But one of them has this further ability to sort of stabilize through resonance. So get really comfortable. Again, if you struggle with electrons and pushing electrons throughout systems, sort of the aromatic chemistry might be a little bit of a challenge because a lot of the things that we'll see in terms of the influences of regiochemistry and so forth will actually be dictated and will be explained through the ability to draw these different types of resonance forms, okay? Okay. All right, so now, if we are to, I sort of show this example over here, where I was able to deprotonate a phenol, and then I did basically oscillation with TBS. Okay, so I in fact did O-alkylation in this case.
Does that work similar to TBDMS?
That's TBS and TBDMS are the same thing. Yeah.
You have to do one equivalent, right? To avoid that.
To avoid silating this one as well? Yeah, maybe. Yeah, it'd probably be smart. Yeah. So okay. So the phenol. So I don't want to confuse you. So the phenol is more reactive. The alkoxide conjugate base is more stable. Right. The conjugate base is more stable. If the acid is more stronger, the conjugate base is more stable. Right. The para is going to be a stronger acid because the conjugate base is more stable. All right, so in the chemistry that your book talks, again, we talked about during enol and enolate chemistry, how, we sort of alluded to the fact previously when we started talking about phenols. We sort of, I guess this wouldn't be resonance, but sort of, yeah, it's resonance. How there's sort of two resonance forms of sort of enolates, right? And we sort of alluded to the fact that alkoxides, that you could sort of do O-alkylation, and you could also do C-alkylation, but primarily we focused almost exclusively on C-alkylation just to sort of keep things simpler. Now in the case of sort of phenols, which are in a way masked enols, right? The book begins to throw a few sort of curveballs at you. So where we start seeing both C alkylation and O alkylation. Okay, and so I'm not going to spend too much time on this, but I'll just sort of talk about the examples that the sort of book uses. Okay, so in general, if you take a phenol and you treat it to a base, again, one of the ones that it uses a lot is sodium hydroxide. Okay, you're going to generate the alkoxide, and then what you can do is you can basically take this and you can treat it with a nucleophile, or sorry, an electrophile. And the book gives a couple examples. Generally, in these cases, what you want to use is what we refer to as like a really hard electrophile. So one of the things the book talks about is like methane. Methyl triflate or methane sulfonate. Okay, so what you're going to do in this case is this is going to serve as your electrophile. You're going to deprotonate, and then that's simply going to attack your alkoxide, right? And the net result is going to be alkylation. So it turns out that you can do alkylations of phenols fairly readily. Yeah. You can. Sometimes, I'm trying to think, because I have done it in the past. Sometimes you'll need like sort of like sodium iodide in there, I think, to actually get it to react. Just sort of make the methyl iodide. If you don't have methyl iodide, sometimes alkyl halides will do that. The book also discusses allyl chloride as an electrophile as well. So, I would say that for the sake of keeping things simple, I would just say, if you take them and you treat them with, let's just, to keep it simple, just say, you can take this, you can treat it with any alkyl halide. We'll just say Rx or some alkyl leaving group. And generally what will happen is you get O alkylation. I've actually never seen C alkylation from these alkyl groups in the past. So I'm prone to believe that you would never do C alkylation in these cases, but I'm sure that there are conditions that you can use that would change it. But to sort of keep things simple, let's just say that unlike an enol, right, if you take an enol and you treat it to certain alkyl halides, you'll often do C alkylation. Although, again, even in cases like methyl triflate and stuff, you can do O, but for what we've learned, C. In the case of this one, what we'll rationalize, right, is that the alkoxide is even more stable in the aromatic form, and so we'll sort of attack from the sort of phenoxide form. Yes?
What about the double nature, double nitrogen?
Double nitrogen in the CH3. Oh yeah, you could do this with diazomethane as well, I believe. Yeah, I mean that's can you do that with diazomethane? Yeah, you might be able to. I think you can. I know that certainly certain ones are. I don't know if phenol by itself would react. I know that if you have like electron withdrawing groups where it's even more acidic, because I know like a lot of the chemistry we do where we have molecules that are phenol-like, you can treat those with diazomethane. pKa's of those are like around 6 though. With diazomethane, no, because it's its own base, right? Because it's a base to make itself into an electrophile, right? So, so let's just sort of keep it simple. Let's just say you can take an alkoxide, so you guys know you can take an phenoxide or phenol, convert it into the phenoxide, and then you can take that and you can treat it with any sort of alkyl halide, and what you'll get to is something like this. Now, here's an interesting sort of, I don't know if we want to call it a twist or not. But the book discusses taking owl. The book discusses taking like owl chloride as your nucleophile. So if you first treat this with sodium hydroxide and then treat it subsequently with owl chloride, what you'll get to is this compound here, right? You'll substitute it with an owl group. Now it turns out that this is an interesting case when you have an owl alcohol in there, because if you take this molecule and you heat it really high, what will happen is you'll actually end up with the owl group right there. Okay? And if, say, for example, we have a substituent, let's say that we can do this and we put a substituent there, right? That substituent will end up right there. So how do you guys think that this might be happening? This would be a good exam question. Yeah. Yeah, Claisen rearrangement, good. Perfect, right? So what's happening in this case is that you're getting a Claisen rearrangement. Everybody see that? So again, get rid of that now. Right, you do the Claisen rearrangement, you go to this, right, and then it's simply an aromatization away. So this is not going to be stable, right, because it's not aromatic, right? So it's going to rapidly aromatize, right? So this proton over here is going to tautomerize very rapidly, right, and you'll end up getting that molecule there. Okay, so certainly with owl groups, they're kind of neat because you can do the O-allylation, but if you want the C-allylation, you can simply use a sort of Claisen rearrangement to effectively get to this product here. Okay? All right. Okay, so first reaction, effectively O-alkylation of phenols. Now, it turns out that, again, when we start talking about benzylic groups, there's another factor that will often come up with them as well, and that's that they're fairly prone to the same way they're able to stabilize cation charges here, anion charges here, you might imagine they'd also be able to stabilize radicals, right? We could push radical mechanisms throughout here and stabilize a radical. And I remember when I was in graduate school, I was running a reaction in toluene, and I went up to like 200 degrees in a seal tube. And it went for a period of time, and when I isolated my sort of atmosphere, but certainly pressurized once you're at high temperatures, I was like at probably about 200 degrees Celsius. And I was running a completely different reaction, but toluene happened to be the solvent. And what I ended up getting out was a lot of benzoic acid. And this is sort of one of my first sort of realizations of two things. First of all, oxygen, especially at high temperatures, can certainly be a sort of a hydrogen radical extractor, but it also sort of put into place for me how prone these are to sort of radical stabilization. So at super high temperatures, the oxygen, I hadn't spurred the reaction, there was still a lot of oxygen there, as you guys might know. Right, oxygen exists in this, what we call triplet state, right? So that's the better way to draw oxygen. It's actually the way that it behaves, right? And so what happened was, we're able to generate this radical, okay? Okay, and the reason why you could generate this toluene radical is, again, through resonance stabilization throughout this ring. So again, I can begin to draw resonance forms throughout here, right, where we begin to have sort of that neutral radical species, and then we could continue to push that radical throughout the system. So again, the radical is stabilized in the same way the anion is or the cation is. In the case of what I was working on, these two effectively combined. And again, this is known to do this. Okay, we'll get to this sort of peroxide, and then the peroxide happened to sort of perhaps you can imagine elimination, followed by oxidation of the aldehyde. Again, this isn't a reaction that we're learning, I'm just sort of using this as an example to illustrate the sort of stability of the sort of radicals. Where your book discusses this a little bit more detail, and what you guys should know, and will be responsible for knowing, is how this type of behavior of radical stability, right, plays itself out within halogenation chemistry. So my professor back when I was at Boston College used to love demonstrations, and one of the demonstrations that he would do for Organic 1 was he would, and to sort of show the stability of aromatic compounds, is he would effectively take a solution of benzene, and he would take a solution you're sort of talking about the stability of aromatic groups. He was trying to sort of illustrate the differences between aromatic alkenes and the sort of alkenes that make up a benzene, and sort of isolated alkenes, and sort of relative reactivity of these two. And so, as the story tells it, for years he would have cyclohexene, and the cyclohexene, he would have this overhead projector, and he would add bromine. And if you guys did the experiment with bromine, maybe last semester, right, there was a red color, and the red color went away when it reacted with alkenes. That was how you guys, I guess, determined that you had made alkenes in an experiment that you did in Organic 1. And so he did this experiment in front of the class, and he had a petri dish, and he sort of projected it, and you would see the red, and you would see the red go away when he added this, but then you wouldn't see the red go away when you added benzene. So there was an interesting story that he told, where I guess one day he came in and he couldn't find benzene, or the graduate student that was getting him the benzene couldn't find benzene, and so they grabbed toluene instead, expecting that toluene would not react with the bromine. But lo and behold, the professor went ahead and began to add the toluene to the solution, expecting it not to change color, and it changed color, right? So while benzene does not react with halogens, turns out that toluene will, but it's a completely different reaction. Okay, when you take toluene and you react it with bromine, what you instead get is bromination, or bromination at the benzyl position. And unlike this case where it's where the alkene is existing as a nucleophile, in this case all that's happening is sort of radical stabilization. Okay? And so what was happening was, excuse me, the bromine, again, I don't know if the story goes if he was heating this or not, but as you've sort of seen, the homolytic bond cleavage of bromine can happen quite readily. And what you can end up with, right, is two bromine radicals. Right, so you can do that homolytic bond cleavage and effectively break the bond and have each bromine carry a single electron. And then what can happen is, again, because of the stability through resonance stabilization, you can now generate a sort of toluene radical, okay? In this case, you're also generating HBr, side product, right? And the leftover bromine radical to then react and generate the sort of benzyl bromide. And so we've seen this, I believe, perhaps you saw this last semester with AL, right? So you might have seen this with bromination with like AL groups per se. But again, it can happen fairly quickly with tolubles, perhaps faster than simple allylic bromination. So benzylic bromination can happen faster than allylic bromination, as you might imagine, due to the sort of stability of the sort of resulting benzyl radical. Okay. Okay. The one other thing that, and again, we'll get back to this in a little bit. But one other thing that I want to talk to, and it's sort of more related to sort of oxidation chemistry, is sort of oxidation of phenols. Okay, so if you have a molecule that's phenol, right? If you have phenol, it turns out that you can sort of oxidize these fairly readily. Well, you need somewhat of a harsh oxidant, but in other cases you can actually do them quite mildly. But if you take a phenol, this is something worth knowing. If you take a phenol and you treat it with really strong oxidizing reagents, so say for example, Jones reagent, what does the book give you? Yeah, so yeah, PCC, I don't know, that's a good question. I would guess no, for no other reason that I haven't seen it done. But again, once you get into sort of oxidants, you can imagine that at higher temperatures it might. So in this case, what's going to happen is, again, and this might be a reason why in this specific case you might, in other cases you might be able to in the sort of 1,4-phenol. But you sort of need water in this case, and what's going to happen is you're going to get to this molecule known as a quinone. Okay, so this is something that might be worth keeping in mind. Where might you think a molecule like this, in terms of chemistry that we've done, might you find value? Right? What kind of molecule would that be with chemistry that we've recently learned? Yeah, Diels-Alder chemistry, right? It might be a really good dipole partner for Diels-Alder chemistry because it's a really electronically poor alkene, right? And so you can imagine certainly doing chemistry with one of those alkenes, right, to sort of generate different compounds. And so certainly having phenols and sort of which are themselves relatively stable, you might be able to oxidize them up to compounds that are perhaps useful synthetic intermediates in other types of reactions. Now, you can also do this, I believe, under milder conditions. Although the book uses the exact same conditions. But if you want to, you have a sort of para-bisphenol, and you do the same thing, you're going to get the same thing. Right, so if you do this chemistry with different bisphenols, yeah. We'll talk about it in a second. So yeah, I mean this can reduce, but not with Jones. You need some type of reductant. Fairly mild reductants will do it. Lithium aluminum hydride. Well, let's discuss that in a second, because that'll be an interesting question. If you have the 1,2, though, you actually get to a different type of quinone. So this is called a quinone. And the sort of standard quinone that we think about is this one. If you have the two groups, what's this? Ortho, right? You can also get to, this is also a quinone. So generally when we talk about a quinone, we're referring to the 1,4 or the para quinone. But sometimes you'll see this one as well. But you have to actually have those phenols in place. But this would be ortho. Okay, so you can get into situations like this. Now, where might this also find value? Same thing, right? Diels-Alder chemistry. But this is an electronically poor diene, right? So you would need a different type of, right? In this case, it would be your sort of normal electron demand Diels-Alder. In this case, now you have an electronically poor diene, so you need an electronically rich alkene or alkyne to react with it. So this would be sort of the inverse electron demand. So you'd want an electronically rich partner, because this is an electronically poor diene. Okay? So the question was basically raised, is this process reversible? Absolutely. You have to be careful about what you sort of use as your reductant. So let's think about what would happen if you, I think that's an interesting sort of thought. Right? We think about our standard reducing agents, and the question was asked, can I reduce this with LAH? What do you guys think? I don't know. I think it's perfectly worth thinking about. And in fact, in this type of situation, we could probably draw a mechanism that might tell us and let us sort of see whether or not we might be able to do it or not. So let's just go through a mechanism. Yeah? Well, there will be a rate limiting step. I would expect, so you bring up a sort of a something relative to reductions of alpha beta unsaturated compounds. So yes, technically we might need to use like a loose reduction or something like that, which is a slight modification. But again, in this case, we're just talking about, just from what you guys know, if you took this and you treated it with some hydride, right, where would that hydride add? Based upon what you guys know. It might add 1,4, but, right, it would hit the carbonyl. Okay, and then what might happen? Well, it might. Yeah, it might just tautomerize, right? This is simply, effectively, a tautomer. Yeah, it probably wouldn't happen. I mean, you could imagine this deprotonating that and setting it off for two molecules come together. This isn't going to actually wrap around and grab that proton, but just for sort of board space and just go through it, and you basically get there, and then when you work it up, yeah. So you might imagine that something like a hydride, your standard reducing conditions, might do it. I think the book uses sodium dithionate, so like the stuff that you use to reduce the osmium tetroxide reaction, for example. So a mild, won't need, this is kind of overkill. Lithium aluminum hydride would definitely be overkill in this case. Usually would be something a lot milder would even do it. And again, it would work based upon, effectively, you can imagine dumping a couple electrons in that system. Yeah, Felix? Yeah, exactly. Yeah, so the point is, in this case, again, the mechanism doesn't really go through the mechanism per se, but you would imagine that in this case you would need water, and the other oxygen would actually come from the water. And again, I could scribble the mechanism up here, but I'd rather do it during office hours if you're curious. Okay, so, all right, so that's probably all I'm going to talk about in terms of chapter 21. Okay, so read all through chapter 21. It also talks about toluene oxidation as well, and so I'll just put them up here really quickly. I do want you guys knowing all these reactions. I'll just scribble down the other two and won't discuss them too much. But you guys should be able to read through them based upon what you know, sort of make sense of these. So one reaction that your book discusses is called a cold synthesis. It's to make like salicylic acid. So if you take this molecule and treat it with sodium hydroxide, and then treat it with pressurized CO2. You can actually get to silicic acid. Okay, so you guys can go through this on your own. It's simply enolate style chemistry with an equivalent of CO2 as being your electrophile. So we've seen CO2 as electrophiles in the past. So this is silicic acid, salicylic acid. No, salicylic acid. Acetyl acid is thank you, aspirin. I need some aspirin right now. So anyway, so that's one that I asked you guys to look up. The other, I sort of discussed this a little bit when we were talking about oxidation of methane stuff, but you know, it's worth noticing. So this is kind of, okay, actually I probably should spend a little bit of time on this. This is a little bit wild, I think, and this is kind of counterintuitive. And the mechanism of this process, I'm not even quite sure. I've got some ideas of how it might go down. I was trying to look up and see if I could find the mechanism of this process. Whether it's radical-based or whether it's this reaction called ene-like chemistry. But if you take a molecule like a toluene compound and you treat it to, again, something like Jones reagent. So again, we see Jones reagent with phenols, but if you simply take toluene and you treat it with a strong oxidant like Jones reagent, what you'll actually do is you'll get the benzoic acid. And this is kind of, I find this kind of interesting, kind of actually, I mean, I don't find this that crazy, but it's this next thing that I kind of find crazy. That if you do the same thing with, say, ethylbenzene, again, what your gut might tell you, if you haven't read ahead in the chapter, based upon oxidation, what might you think that you would get? Yeah, you might expect that you would get the ketone, right? And I think that, if you guys said ketone, I'd be like, great. That would sort of make sense based upon what you know. In fact, this will also go to the carboxylic acid. And your book sort of says this in the text, but really doesn't show it that much. But if you actually have an ethyl group here, you get this. I don't know if the byproduct is ethanol. I don't know if the mechanism is Baeyer-Villiger oxidation-like, subsequently after you generate the ketone, perhaps. I'm really not sure, but that's sort of what's formed. Basically, as long as you have a proton at that position, you'll do oxidation of these sort of alkyl benzenes all the way up to the carboxylic acid. So if you don't have a proton there, so let's say, for example, if you have p-butyl, you actually get no reaction. So if you have a benzyl group, if you have benzylic protons, and you treat it to these sort of highly oxidative conditions, what will actually happen is you'll oxidize, and you can actually oxidize all the way up to the carboxylic acid. And I think that's perhaps a little bit counterintuitive, right? Because you might imagine, based upon what we said, it would sort of stop the ketone. But through some mechanism, which I'm guessing, again, there's a reaction called Baeyer-Villiger oxidation, which might be, if you guys are curious, which might result in the subsequent oxidation. Not really clear, but so I'm not going to necessarily hold you responsible that mechanism. But it's worth knowing, at least from a synthesis standpoint, that if you want to oxidize to sort of benzoic acids, you can really have any alkyl group here. And so that's also a nice kind of way to break carbon-carbon bonds, yes? Yeah, that's what I'm saying. I think it's probably leaves as like methanol. Yeah, so I think that my guess, again, I'm not sure, but my guess is there's an intermediate. My guess is that that's an intermediate. So again, I'm not going to hold you responsible for this, but if you're really curious, my bet is that it goes through the ketone, and then you can look up a Baeyer-Villiger oxidation. So it probably goes to the ketone and then oxidizes further, but I'm not sure. I actually don't know. So you're not responsible for knowing that mechanism, but you are responsible for sort of knowing that these will oxidize as long as you have the proton, a proton benzylic, you'll oxidize all the way to the carboxylic acid. Okay? All right, wow. 15 minutes left. All right. And we're just getting into the next chapter. Okay, well, I was hoping to already be at this chapter like a half hour ago. So, all right, so let's get to reactions. Actually, the timing might work out well. Because now what we're really going to talk about is, we've talked about sort of some chemistry on benzenes, but now what we're going to get to is reactions, sort of like alkylations and so forth of benzene. So like we just said earlier, right, if you take benzene and you react it with bromine, right, you're not going to get any reaction, right? If you take benzene, you react it with bromine, you're not going to get any reaction. Why might you think that this is the case? Just intuitively, why might you think? Yeah. Well, I mean, yeah, this is really stable, right? And what you're doing, right, if you were to say, for example, react this with bromine, yeah, I mean, you're sort of breaking the aromaticity. So it's a huge uphill barrier because not only are you sort of creating a cation, right, but you're actually breaking the aromaticity, which we spent so much time discussing is so stable, right? So this will not happen. And in order to get, but obviously we have a whole chapter that's going to be devoted to sort of breaking aromaticity and making bonds. So we can do it, but what we need to do is we need to have a really, really, really good electrophile. Okay? And what we do, if we want to say, for example, brominate, or let's say, right, if we want to add bromine to this, and again, as I'm going through the mechanism, you'll see that sort of dibromides could form, but the aromaticity, retaining aromaticity, will be favored. What we effectively want to generate, and this will be like a theme throughout this chapter, is we really want to generate bromine plus, in a way. And this will sort of be a theme. We'll really want to generate these highly electrophilic charged species, right? So the way that we're going to do this, in essence, again, we're not actually generating bromine plus, but it's sort of worth it to keep that in mind as we're trying to generate great electrophiles, is we're going to use bromine with some type of really good Lewis acid. And the one that the book uses is iron trichloride. Okay? Iron trichloride is a really good Lewis acid. It's sort of like, again, it's transition metal, so it's not exactly like boron trichloride, but it's willing to sort of accept electrons. And what happens is, effectively a set of electrons on that bromine, right? Again, the iron trichloride is really, really good Lewis base. It's going to sort of coordinate to that iron trichloride, okay? And what we're going to get to the molecule that we can think about is this form, but even more likely we can think about it like what I said before, as ER plus ER FeCl3 minus. Okay? So we can start to think about the iron. Again, it's a transition metal, so it might not be the best parallel, but we can think about, again, boron, for example, wanting to take on a couple extra electrons and be a really good Lewis acid. And what that's going to allow us to get to is, in essence, a much stronger electrophile than bromine is by itself. And again, if you sort of think about it in this form, you can sort of use this moving forward in a lot of the chemistry that we're going to see, sort of positively charged electrophiles for aromatic chemistry. Okay? So in this case, what we're effectively doing, right, is under that reaction condition, Br2 FeCl3, as you can imagine it reacting with bromine plus now. Okay. We're now going to break the aromaticity. And at this point, we have a couple options, right? We still have this FeCl3 bromide. Okay, so we can, perhaps think about it. Again, it's going to be reversible in a way. We can at least think about it in a couple different forms. But just for sort of electron arrow pushing, we can sort of think about it as molecular bromine. Again, we can think about the Br minus. The bromine has two options here, right? That bromine could either attack here, just as it would with, say, for example, an alkene, right, where we generate the dibromide. Or what we can do is E2 chemistry. So SN1 or E1. Okay? And of those two options, right, the E1 is going to be favored, right? And why do you guys think that would be? Because aromatic groups are really, really good, and if you can regenerate the aromatic group, it will happen, right? So it's going to go the E1 pathway, and what you're going to get is this sort of bromide, okay? So the idea here, the sort of take-home lesson, and I'll show one more reaction that sort of falls under this sort of umbrella, is that bromine itself is not a good enough electrophile to react with benzene. However, benzene can behave in a similar way with an alkene. You just need a much, much better electrophile. And in this case, you can take bromine and effectively turn it into a much better electrophile by treating it with a really, really good Lewis acid. Okay? I'll show one more example. Yes? You've got a carbocation intermediate. So it would be E1. E2 is at the same time. Yeah. Wasn't really the point that but so you see the elimination is the important point. Substitution versus elimination. But you could also write an SN2 like mechanism, or an E2 like mechanism too, right? You could just have the bromine attack and then actually do. The important point is you get the aromatic compound because the aromatic one is more stable. Okay. So again, this is bromination, but as it turns out, you can also do alkylation of benzene in a similar case. Now, again, if we transition from bromine, right, and we want to make an alkyl aryl bond, we might imagine an alkyl bromide, right? But if bromine is not going to react with an alkene, an alkyl bromide is not going to react with benzene, right? So again, in this case, effectively what we want to do is very analogous. We want to generate what is in essence a cationic species, okay? And so we're going to use the same thing, FeCl3, or I think the book says aluminum trichloride, so we'll stick with aluminum trichloride. But again, it's the same idea, a really strong Lewis acid. It's going to take this molecule, okay? It's going to effectively pull the bromine away in the same way that we did it from the other bromine. And what's going to happen is we're going to be left with R plus right, is that same thing, right? So if you take, yes? I think you can actually use them interchangeably, yeah. But the idea, again, the important point is that you have some really good Lewis acid that's able to effectively coordinate to the leaving group and help it assist, right, in being a leaving group. And so, whether the mechanism actually involves this or not is kind of, at least we can think about it this way. Right, and so now, again, we can react. Right, and in the same way as before, what's going to happen is we'll then do the elimination. Is that, okay? And so there's a few different classes of these. I'll just go over those and let you guys go. So this is the general idea, is you're making a carbon-carbon bond on the aromatic group. Again, it should be just as analogous as the bromination chemistry. Lewis acid coordinates the halide, makes the other aspect of that electrophile, cation in character, allows the benzene to react. Okay? And so there's a few classes of these that we'll discuss, and so I'll give you the names of them. Okay? These all sort of fall under the name of Friedel-Crafts. Okay? So, in this case, if the R is your standard alkyl group, this would be Friedel-Crafts alkylation. Okay? In the case of Friedel-Crafts acylation, the difference is that you have an acid chloride. Okay? So if you do the same chemistry with aluminum trichloride, okay? Again, these are going to react together. You're going to generate sort of oxonium here. Again, that's just the resonance stabilized form of if you plucked it off, right? And I just draw it in this form. Right, so this is simply a resonance form of. Right, so all I've done is made that cation and sort of just drawn it in that other oxonium form. Why do you guys think I decided to draw it in the oxonium form? Why did I want to draw it like this rather than this? What'd you say? Yeah, full octet. This one has a full octet. So generally, if you can draw it with a full octet, you want it. Okay, and then same thing's going to happen, right? This is going to attack here. Okay, and I just want to tell you guys one more. It doesn't really formally have a name, but I think it sort of falls under this umbrella of cation formation. How else do you guys know to make alkyl cations? How have we made alkyl cations in the past? Nope, that's NaNH2 is a base. So we've seen alkyl cations generated a few ways in the past, right? One is to have an alkyl halide and have that leave, right? Or to have an OH and have it leave as water. But there's another way that we've generated them, that's from alkenes. And so I just wanted to sort of stop here. That the other way that you can do this is to take, if you say, for example, have an alkene, and you're under really acidic conditions, right? You can generate, right, that cation. Right, so this is just another way to get entry into these types of systems. You can generate a cation, and again, these cations can be reactive enough. And then you're simply going to do the elimination, right, to get there. So again, all these should be sort of analogous. The whole idea is benzene is unreactive but if you have a very highly cationic species, you can react with it. So one quick announcement. Again, I'll make this announcement again on Wednesday, but this upcoming Friday, we had a speaker this last Friday. I saw a few of you there. There's another one this upcoming Friday that's actually a collaborator of mine. He's going to be talking about HIV and resistance pathways. And what's interesting is that at 2 o'clock, we're sort of doing a roundtable where undergrads can sort of ask him questions from 2 to 2:30 before his talk. So I highly recommend you guys, there'll be flyers for it, so just keep an eye out if you're interested.